Today what we're going to be looking at is the idea of Beer's law. Now before we can get to Beer's law, we have to understand what's going on. What we're going to be trying to do is examine a molecule by the light that it absorbs. So if it is absorbing light, we'd better be sure that we have light that it actually absorbs. So what I have here is a graph of two different substances. One is chlorophyll here, and one is carotenoids. Or carotenoids, I don't know, tomato, which might actually be carotenoids. Anyway, what you've got here is you've got two different substances, chlorophyll and the carotenoids. And you can see that when solutions of these are exposed to different wavelengths of visible light, and yes, it works with other aspects of the electromagnetic radiation as well, it's just we're going to be focusing on the visible spectrum, which is why we're going to go from about 400 or so to about 700 or so, because that is the wavelength in nanometers of the visible light, you know, from Roy G. Biv all the way from there. Anyway, if you check out chlorophyll, a chlorophyll molecule kind of looks like this and has all manner of different bonds and so forth. And a carotenoid molecule over here is a different molecule. And because they are different molecules with different bonds and different arrangements, they are going to interact with energies of different wavelengths differently. So consequently, chlorophyll apparently has a very strong absorption around this spot right here in the blue spectrum, right? And also has a pretty high absorption way over here in the red spectrum. So if you wanted to examine chlorophyll, you would want to set your device so that it is somewhere in the, 450-ish zone, give or take a little. You've got a little leeway in here, somewhere in there, or you want to set it in the, what's that going to be, about 675-ish zone, somewhere there. That is going to give you your best response. Now, could you do it here? Sure. Could you do it here? Sure. And sometimes your device is limited on the actual wavelengths that you get to choose, but either of those choices, anywhere around either here or here, would be a fine choice for the chlorophyll. If you're going to do a carotenoid, it looks like you've got pretty much anywhere from in here to in here. You could pick any of those spots in there. So that looks like it's going to be somewhere around the, 490-ish, or in here it looks like it's going to be around the 520-ish, somewhere in there. But if you're going to do a carotenoid, and you have it set over here, well, you're not going to get any response because there is no response in a carotenoid to this particular wavelength. If you're going to set it over here for a carotenoid, then again, it's probably not going to give a very good response. So what you want to make sure that you do is you set your device to one of these wavelengths that is going to give a high absorption. So our first step that we have to do when doing any manner of Beer's law investigation is to develop a graph like this. And what you need is a device that will scan a sample of your material, and it will scan it from 400 or so to 700 or so, and tell you which of these wavelengths is a high absorption and which of these wavelengths is a low absorption, so you can then tailor your investigation to pick something that is going to be up here near the top of the scale and not near the bottom. Because again, if you're going to investigate chlorophyll, you don't want to pick somewhere around the 550 zone. You're not getting a very good response there. If you're going to pick a carotenoid, then you don't want to pick somewhere over here. That's not going to do you much good. If you're going to do a carotenoid, then you want to make sure that you pick somewhere up here, or if you're going to do chlorophyll, you want to make sure that you do somewhere up here. So our first job is to develop one of these. So what we're going to do now is we're going to see if we can't get a spectrum of our unknown sample. Now we are using the Gatorade Frost Cool Thirst Quencher Glacier Freeze, and you can tell that it's a bluish color there. So it's going to give us a particular spectrum, I should say. So what we're going to do is we're going to use one of these guys, which is a Go Direct SpectroViz Plus. And it's got a beam in there that will fire all manner of wavelength of light at a sample. and tell you which ones are absorbing it and which ones are not, right? So I've got my program set up here, and all it's got to do is finish calibrating. So it wants me to put a blank cuvette in the device. So here is the cuvette. Thing about cuvettes, if you notice, is that one of the sides, I don't know if you can tell here or not, but two of the sides are a little frosty and two of the sides are clear. So you want to make sure that the clear sides go in. So I have now put it in so that the clear sides are going left to right here, because that's the way that the laser is going. You don't want the frosted sides to get in the way. That will screw up your results. So that's just water. That's a blank cuvette with water in there. And it says, okay, great, finish the calibration. So I'll finish the calibration. And what that is doing is basically tearing the scale. It is telling the computer to ignore water, and it's telling it to ignore the plastic device, the cuvette it's called. All right, and you can tell, if I hit collect here, that nothing is happening. So it is not absorbing anything because, again, it is, we are telling it to ignore all of these things. So I've got a couple of samples over here just for comparison purposes. Here is one here, and here is one here, and you can tell that they are very different samples, right? One of them is kind of reddish, and one of them is kind of purplish. So let's see what happens when we put these into the spectrometer here. So if I put the red one into the spectrometer, now I am getting results that look like this. And I am certainly getting some absorption over here, and I am not getting any absorption over here. Now if I take that out and then compare it to the purple one, let's see what happens. So there is the purple one that I now have in. So here is the purple one, and the purple one is giving a very different result than the other one, right? So each of these substances is giving a different response to the wavelengths of light that are happening there. So now what we're going to do is we are going to attempt to do a real experiment here with our Gatorade here. So I have restarted the program. I have got myself a brand new cuvette, again with blank water in it. That's a pretty good shot. You can see the frosted sides and you can see the clear sides. So I'm going to go ahead and put this guy into our spectrometer here, like so. And it wants me to finish the calibration for it. So fine, I'll finish the calibration for it. There we go. And we are at a blank here. We are in good shape to go. And I'm going to take the blank cuvette that I just did, and I'm going to empty it out. All right, because theoretically, technically you're supposed to use the exact same device each time because of small variations in things. Now there might actually still be some water in here. So what I am going to do is I am going to fill this with some of our Gatorade solution, and then I'm going to dump it out. And that's going to get rid of all the extra of anything that was in there before. So I'm going to fill it with the Gatorade solution, and I'm going to dump it out. And then one more time, I'm going to fill it with the Gatorade solution one last time. And then you just got to make sure that everything is wiped clean, because you don't want any smudges or anything like that in the way. Because if there are smudges on the clear side of your cuvette, that will absorb more light. You also don't want any bubbles or anything in there, because bubbles will diffract the light and do that as well. So you want to make sure that it is as smudge and bubble free, because those things will affect your absorption. So anyway, now I've got this guy filled with just my Gatorade. So I'm going to come back over here, and I am going to put him into the SpectroViz thing here, and then I'm going to come over here and I'm going to click collect. And it has now collected my sample. It doesn't look like it's particularly strong, but that's okay. It will scale it up once we go ahead and hit stop here. So it looks like it's good. We're done. I'm going to go ahead and hit stop. And like I said, it scaled it up to a proper amount there on the screen. So that there is the absorption for our Gatorade. So if we had our choice of any wavelength at all, which wavelength would we need to choose in order to make this work? So go ahead and pause your screen there and see if you can't figure that out. Which wavelength is going to be best for determining this? All right, so this is our absorption spectrum. And if we had a perfect world, we would pick something right at the top of either of those peaks. Now, it's not a perfect world. We are limited by the devices that we have, and the devices that we have look like this. They only give us 3 different options for absorbing things. We can do things at 565, we can do things at 635, or we can do things at 470 there. So which one of these choices, the 565, the 635, or the 470, is going to be the best for us to examine this substance? Well, first of all, let's look at 565. So we come over here and check out our screen. 565, find that one. That's not going to be too terrible. So 565 is going to be somewhere around here. We're getting something out of it. All right. What about the other ones? Let's see, 470 for the blue. Let's see, 470 for the blue is going to be right around here. Again, we could probably get some data that way. But then what about the middle one? What about the red, the 635 nanometers? If we check out the 635 nanometers, that's going to be right. Oh, you know what? That's just about perfect, actually. Our 635 goes nearly all the way up to the top. So when we do this experiment and we go to do the investigations on things, we are going to want to make sure that this is set to the red setting, because the 635 nanometers for the red is going to give us the highest response from this particular graph.